All right, settle in, everyone. We're going deep today. We're not just talking about using these powerful AI models, but really digging into the theory, the foundations. Why do they work? And maybe more importantly, what guarantees do we actually have? We've got a pile of sources here, a preprint paper, a study guide, briefing doc, a timeline too, all pointing towards a pretty significant breakthrough in understanding transformers theoretically.
You know these models, right? They're behind so much of the AI you interact with. So our mission today is to unpack this research, specifically a key proof, something that gets right to the heart of whether transformers can, reliably learn. Do they actually converge to the best possible result, especially when the data isn't, well, flat?
And that reliability question, it's absolutely central. It really is. Transformers are honestly incredibly successful in practice. Nobody denies that. Their empirical results are just stunning. But theoretically, understanding why they're such effective learners, whether they're fundamental guarantees they'll find the best solution if you give them enough data, that's been a crucial, partly unanswered question. This paper tackles that directly. It goes beyond just saying transformers can represent functions. It tries to prove they can learn them optimally, under certain conditions, of course. And what's really novel, I think, is they tackle this not just for standard flat data, but for data in curved non-Euclidean spaces. And then, the really neat part, they show how the guarantee for the standard transformer we all use actually pops out as a special case. It's like solidifying the science behind the amazing engineering.
Okay, makes sense. So before we dive into the deep end, let's just quickly touch base on the standard transformer. Just a quick recap for protext based on our sources. Right. So think back to their start. Processing sequences like text. You've got two main parts, an encoder and a decoder. The encoder, it takes your input, uses self-attention to figure out how all the pieces relate to each other, passes that through some neural network layers. Standard stuff.
The decoder does something similar, but it also looks at
What the encoder found that's cross attention, and it's careful not to cheat by looking ahead in the sequence it's trying to generate. Masked self attention.
exactly.
And the absolute core, the big innovation when they first appeared, was that attention mechanism. Instead of just processing word by word linearly like older models, attention lets the model weigh the importance of every other word when it's looking at one specific word.
He gets to look around.
Yeah, it decides what's relevant right now to understand this piece. The sources remind us the math involves these query, key, and value things deriving the input, and using softmax to turn those relationships into weights. That dynamic weighting is the magic, really, getting those rich, context-aware representations.
Precisely. And for a long time, theoretical work on neural nets in general, and then specifically on transformers, it really focused heavily on this idea of universal approximation. There were classic results back in the late 80s, early 90s for neural networks, and later work specifically for transformers, showing they have the capacity to represent basically any function you want if they're big enough. You can think of it maybe like knowing an artist can technically paint any picture imaginable. They have the raw ability, the tools, the potential.
Okay, they can do it.
Right, but that's very different from universal consistency. Consistency asks a much harder question. It asks, if you give the learning algorithm enough training data, will it actually learn the best possible function for that problem? Will it converge to the true optimal solution as you give it more and more examples? This is about the learning process itself being reliable, asymptotically optimal.
So not just can they paint it, but will they learn to paint the specific masterpiece you want if you show them enough examples?
Exactly. Will they get asymptotically as good as possible at that specific task? And for complex models like transformers, especially doing things like sequence prediction, and especially when dealing with data that doesn't fit neatly into flat Euclidean space, proving universal consistency was a major open problem, a big theoretical gap. This paper makes a real stride in filling that gap, providing a strong guarantee about what transformers can actually learn reliably.
Which leads us right into this idea of non-Euclidean space. You mentioned it. The sources really highlight this. Real-world data isn't always, flat like a grid. Think about hierarchies, categories within categories, or network structures like social connections. These often have, as the sources put it, an inherently non-Euclidean geometry.
Spot on. And that's where hyperbolic space comes into play.
So what is hyperbolic space, simply?
Well, Euclidean space is our normal intuition. Flat. The shortest distance is a straight line. Parallel lines stay parallel forever. Hyperbolic space is different. It's a type of non-Euclidean space, one with constant negative curvature. Imagine trying to draw in a saddle shape. Triangles have angles adding up to less than 180 degrees. Space kind of expands away from you faster.
Okay, harder to picture.
It is. The paper uses a specific model to help visualize and calculate the point array ball model. So all your data points live inside a disk or a sphere. And the shortest paths between points, the straight lines or geodesics, they aren't straight in the Euclidean sense. They're curved arcs that hit the edge of the disk at a right angle.
Arcs of straight lines, okay.
It sounds weird, but it's mathematically consistent. The sources mention the Killinghop theorem, which basically says different models of hyperbolic space are equivalent. So using the Poincare ball is fine, it works. But, and this is crucial, you can't just use your standard vector addition or multiplication inside this curved ball. The geometry is different.
Right, the usual math breaks.
It doesn't apply directly, yeah. You need special tools. Adaptations of standard operations that respect the curvature. The paper uses established math frameworks for this. Things like Mobius addition, Mobius scalar multiplication, ways to add points and scale them within the ball. And importantly, ways to map points from the curved space to a temporary flat tangent space at a point, do some calculations there maybe, and then map back. These are called exponential and logarithmic maps in this context.
So specialized math tools for a curved space.
Exactly. You need them to do anything meaningful, like building a neural network layer that operates correctly in that space.
Okay, so we have the problem. Proving consistency, we have the space. Hyperbolic geometry for complex data, and we have the tools, the special math. The paper's big innovation, then, is the hyperbolic transformer, the HiT.
That's the one, the HiT.
And its purpose is, well, to be a transformer that works natively on data embedded in hyperbolic space, right?
Precisely.
So how did they build it? Did they just swap out some parts?
Essentially, yes, but carefully. They take the standard transformer architecture, the encoder blocks specifically in this work, and they adopt the key layers using that hyperbolic math we just discussed.
Okay, so the inputs, the tokens, they get embedded directly into the Poincare ball, not a flat vector space.
Correct. They start in the curved space.
And then the main layers, self-attention, feed forward.
They become hyperbolic versions. So you have a hyperbolic self-attention layer, hypadat, and a fully hyperbolic feed-forward network, hypss. These layers are built using those operations like Mobius addition for things like skip connections, and using the exponential law maps to move between the ball and tangent spaces for certain computations. It's all designed to respect the hyperbolic geometry.
And they mentioned positional encoding too.
Yes, they include a learnable hyperbolic positional encoding. So even how sequence order is represented is adapted to the curved space.
Got it. Very thorough adaptation.
It needs to be to make the theoretical claims work. And that leads us to the main result, the core breakthrough. Theorem v.1 in the paper. They prove that this specific hyperbolic transformer, the HiT, using standard softmax attention, is strongly universally consistent.
Okay, break that down again. Strong universal consistency means?
It means that as you feed it more and more data, as the number of input tokens, WOT, goes to infinity, the error the HiT makes on its training data will converge, almost surely, meaning with probability 1, to the absolute minimum possible error for that problem, the true generalization error.
So it will learn the best possible solution given enough data.
Exactly. In the limit, it becomes the optimal predictor for that data distribution. This is a really powerful theoretical guarantee. For a complex model like a transformer in this non-Euclidean setting, it's a big deal. It shows it's fundamentally sound as a learner.
And then there was that connection back to the regular transformer.
Ah, yes, this is maybe the most striking part, highlighted in their remark v.1, because they built and proved this for hyperbolic space, which has this curvature parameter c. They found that if you mathematically let that curvature c go to 0, the hyperbolic space essentially becomes flat Euclidean space.
It flattens out.
Right, and their proof still holds. So the universal consistency of the conventional standard Euclidean transformer, the one everyone uses, falls out as a special case of their hyperbolic theorem.
Wow.
Yeah, so by tackling the harder, more general curve case, they ended up providing this fundamental guarantee for the standard transformer too. It helps explain why it works so well, theoretically.
That's actually really elegant. Solve the harder problem and get the simpler one, essentially for free.
Pretty much. It provides a unified theoretical justification.
Okay. Now, the paper mentions this proof relies on certain conditions holding as the amount of data increases, right? As t goes to infinity, the math looked pretty dense.
It is quite technical, yes, but remark v.2 gives the intuition.
What's the gist?
Well, think of them as necessary guardrails for the learning process to behave well in the long run. They basically ensure three things. First, how the data points are distributed within that Poincare ball matters. They can't be clustered too badly, essentially. Second, you just need enough data. The number of tokens T needs to grow sufficiently fast relative to some other parameters. Makes sense, right? More data helps.
Sure.
And third, this is a classic concept in learning theory. The complexity of your model, how flexible or powerful it is, measured by things like pseudo-dimension or metric entropy in the paper, can't grow too fast compared to the amount of data you have.
The model can't get too complex too quickly for the data available?
Exactly. If it does, it might just memorize the training data instead of learning the underlying pattern. These conditions ensure good balance, allowing the model to actually generalize and converge properly. They are the theoretical checks and balances.
Okay, that makes intuitive sense.
And beyond just proving that it converges, the paper also gives us a sense of how fast it converges. They quantify the rate.
Ah, the sample complexity part.
Right. They derive a rate at which the empirical error, the error on the training data, approaches the true generalization error. And that rate is OT.
Okay, T is number of tokens, D is embedding dimension.
Correct. T is your sample size, D is the embedding dimensionality.
So what does that rate tell us practically?
It gives you a theoretical speed limit, in a way. It suggests how quickly you should expect the model's performance to improve as you feed it more data. And it shows that improvement slows down as the dimensionality gets higher, which also makes sense. Higher dimensions are harder to learn in. The sources point out this kind of rate actually matches up pretty well, conceptually at least, with the scaling laws people observe empirically with large language models. Add more data, performance improves, but maybe with diminishing returns. This provides a potential theoretical underpinning for that.
Theory is great, but seeing it in action is better. They did run experiments, right, to back this up.
They did. Crucial step.
So what was the setup?
They used a fairly minimal transformer, an encoder-only model, kind of like dirt, to keep things focused.
And tested different curvatures?
Yep. C equals 0.0 for standard Euclidean, and then a few hyperbolic curvatures, 0.0001, 1.0, and 10.0. So slightly curved, moderately curved, and very curved.
What kind of data?
They used a few question-answering data sets. Squad, which is about extracting answers from text. BullQ, which is binary yes-no questions. And TweetQA, which uses tweets, so it's much noisier, more like real-world messy text. A good mix.
Okay, and the results. Let's look at figure 1 first, the test error over training time.
The main takeaway from figure 1, plotting test RMSE against training epochs, was pretty clear. The hyperbolic models, the ones with C0, generally achieve lower test error, better performance on unseen data than the standard Euclidean model, C equals 0 point out.
So the curve geometry seemed to help.
It seemed to, yeah, especially as training went on. They did note some nuance, sometimes very high curvature, like CE's 10. Didn't do quite as well as moderate curvature, suggesting there might be a sweet spot depending on the data's actual structure.
Interesting. And figure 2, that was testing the convergence rate, right? The sample complexity.
Exactly. That one plotted the test error against the number of training tokens used, specifically on the noisy TweetQI dataset. They compared the actual error curves to a theoretical reference curve decaying at roughly that TA Heather rate.
And did it match?
What they observed was that the empirical error curves consistently stayed below that theoretical reference curve, up to some scaling factor.
So the performance improved at least as fast as the theory predicted.
That's the interpretation. It provides empirical corroboration for that theoretical convergence rate. So overall, the experiments, even with a simplified setup, lend good support to the theory, both the potential benefit of hyperbolic geometry and the predicted learning rate.
It's always nice when the math and the practice align like that.
Definitely reassuring. So wrapping things up, the main achievement here is really establishing this strong theoretical foundation, universal consistency, proving it for both the standard vanilla transformer and this new hyperbolic transformer. It moves them beyond just, wow, they work well, to, okay, we have guarantees they're asymptotically optimal learners. Give it enough data, they will find the best solution.
Solidifies their status.
Right. And extending this into hyperbolic space specifically opens up theoretically grounded ways to tackle data with inherent hierarchies or graph structures, data that isn't naturally flat. Now, of course, there are limitations acknowledged in the paper. The proofs often rely on idealized settings, assumptions like IID, data, which isn't always true in the real world.
Standard practice and theoretical work, usually. Start simple.
Exactly. And they point towards future work, getting tighter bounds, handling non-IID data, looking at how these guarantees translate to actual downstream task performance. Lots more to explore building on this foundation.
So for you listening, the core takeaway from this deep dive, transformers aren't just empirically amazing. There's now some serious math backing them up. This research provides a powerful guarantee with enough data, they are theoretically proven to converge towards the best possible predictor. They are, in a sense, consistent learners.
And that leads to a final thought to maybe chew on. How might understanding these deep theoretical guarantees, knowing that a model architecture is fundamentally wired, in a way, to find the optimal solution, how might that influence how we design, trust, and deploy AI in the future? Especially as we inevitably encounter more and more data with these complex non-Euclidean structures out there in the real world. Does this theory give us new leverage?
A very interesting question indeed, something to think about. Thanks for joining us on this deep dive.